basic concepts that is needed for deriving the expression for acceptance angle and numerical aperture yesterday itself. So those who want to refresh your knowledge, you can please check up the recording once again. It was already posted in your Google Classroom. If you want, you can please go through it. So let us go with the derivation in this session. So let us consider an optical fiber into which light is transmitted. So you are considering an optical fiber and you are going to pass light into it. Let the refractive index of the core is N1 and cladding is N2 and air is N0 such that N1 is greater than N2 and that is greater than N0. So this is the relation between the refractive index of core, cladding and air, right? N1 is the refractive index of core which is larger, N2 is the refractive index of cladding which is less than core, and N0 is the refractive index of air which is less than both core and cladding, right? So this is a relation that connects the refractive index of core, cladding as well as the surrounding medium air. Let the light ray enter the fiber at an angle of theta I to the axis of the fiber. We had given the sketch already. So this is our optical fiber. This represents the core, and this represents the cladding, right? So the refractive index of core is N1, refractive index of cladding is N2, and the refractive index of the surrounding medium is N0, right? So this is the dashed line at the center represents the axis of the fiber, and theta I is the angle of incidence. You are passing a light ray from air to the air core interface, right? The light ray hits the air core interface at the point A. You already know angle of incidence is nothing but angle between the incident light ray and the normal. Since this represents interface, right? So a vertical line over here will represent the interface between air and core, and hence the axis represents normal. This is incident light ray. So this angle represents theta I, right? This represents theta I, that is angle of incidence. So let a light ray enter the fiber at an angle of theta I to the axis of the fiber. The ray refracts at an angle of theta R and strikes the core cladding interface at an angle of phi. Right? So theta I is the angle of incidence at the point A, that is at air core interface, and theta R is the angle of refraction. Since light is passed from air medium to the core medium, air is having a less refractive index, so this acts as a rarer medium, and your core acts as a denser medium. So when light is passed from rarer medium to denser medium, there is you cannot expect total internal reflection to happen, right? Because the condition for total internal reflection says that light should travel from denser medium to rarer medium, but here it is in contradiction. Light is traveling from air medium to the core medium. Air is a rarer medium and core is a denser medium, so you don't expect any total internal reflection to happen at the point A. So the light ray will be completely refracted into the core, right? And theta R is the angle of refraction. You know, this is the refracted ray, this is the normal angle between the refracted light ray and the normal, you call it as angle of refraction. So theta I represents angle of this, theta I represents angle of incidence, and this theta R represents angle of refraction. Let this refracted light ray hit the core cladding interface, right? You know, this is the central core and this is your cladding, right? So this represents the interface between the core and cladding, right? This is core, this is cladding, so this represents the interface between core and cladding. Let this refracted light ray fall at the point B in the core cladding interface, right? This is your core cladding interface. Let the refracted ray falls on the core cladding interface at the point B. So here for the point B, the angle of incidence is, again you need to remember which is normal and which is the interface. So this is your core, this is your cladding, this represents your interface. A line which is drawn perpendicular to this interface represents normal, right? So this line represents normal. So this is your incident light ray, this is your normal. So angle between the incident light ray and the normal, this you call it as angle of incidence. Let us take it as phi. Angle of incidence at the air core interface is theta I, and angle of incidence at the core cladding interface is phi. So you can see it over here. Let the light ray enter the fiber at an angle of theta I to the axis of the fiber. The ray refracts at an angle of theta R and strikes the core cladding interface at an angle of phi. So if phi is greater than phi c, the second condition for total internal reflection says angle of incidence should be greater than critical angle, right? So if phi is greater than phi c, where here phi represents the angle of incidence at the core cladding interface and phi c represents critical angle. So if phi is greater than phi c, the ray will undergo total internal reflection at the interface since n1 is greater than n2, right? At the point B, the two conditions for total internal reflection is satisfied. Could somebody tell me what is the first condition for total internal reflection to happen?
Light should travel from denser to rarer medium.
Yes, exactly. Light should travel from denser medium to rarer medium, core being denser medium and cladding being rarer medium. Here light is falling from core to cladding, right? At the interface, light is falling from core towards the cladding. So the first condition for total internal reflection, that is light should travel from denser medium to rarer medium, is satisfied. And if the value of this angle of incidence, right, if the value of this angle of incidence is greater than critical angle, then the second condition for total internal reflection will also be satisfied, and the light ray will be, as a result, the light ray will be totally internally reflected back into the core itself, right? This process we call it as total internal reflection. So if phi is greater than phi c, the ray undergoes total internal reflection at the interface since n1 is greater than n2. As long as phi is greater than phi c, the light stays within the fiber, right? So wherever the light ray hits the core cladding interface, here also the angle of incidence should be, here this will be angle of incidence, right? If you draw a normal over here, this will represent angle of incidence. That angle of incidence also should be greater than critical angle, right? If that condition is satisfied, then this light will be totally internally reflected back again and again into the fiber and thus received at the far end of the fiber, right? So let us now compute the incident angle theta I, for which phi is greater than or equal to phi c, right? So what happens if phi is equal to phi c? Yes, what happens to the ray of light? See, if phi is greater than phi c, it is just totally internally reflected. If phi is less than phi c, it will be refracted into the cladding and away from the fiber. What happens if the angle of incidence phi is exactly equal to the critical angle phi c?
It graces the interface between denser and
Exactly,
rarer.
exactly, exactly. Good answer. The light ray will just graze the interface between core and cladding, right? The light ray, instead of being totally internally reflected back, it will be just grazing over this interface. The light will take this path, right? That will happen when phi is equal to phi c, right? So let us now compute the incident angle theta I, for which phi is greater than or equal to phi c, such that the light rebounds within the fiber, right? Applying Snell's law at the point A, you can please take it up in your notebook. Let us try to compute the incident angle theta I. Please write it down. This is another important derivation in this part of your syllabus. So please try to take up proper notes. Let us now compute. Please take up today's date as 11/1/2022. I hope you might have already drawn the diagram, or else you can take a screenshot of it. Shall we go on into the derivation?
Yes, ma'am.
Yes. So let us try to compute the incident angle for which this phi is greater than phi c. You already know what is the relation between theta I and phi. If you change the value of theta I, phi, the value of phi will change, right? So let us try to compute what is the value of theta I that is needed to make this phi to stay above phi c, right? So let us try to apply Snell's law at the point A. This is your point A, right? Here you are applying Snell's law. Here the angle of, I mean, the light is incident from the air medium and it gets refracted into the core medium. The refractive index of air is N0 and the refractive index of core is N1. So how will you write Snell's law? N0 sine theta I is equal to N1 sine theta R. I hope it makes sense to you. Snell's law at the point A, applying Snell's law at the point A, we can write n naught sine theta I is equal to n1 sine theta r, where theta I is the angle of incidence at the point A and theta r is the angle of refraction at the same point A. N naught is the refractive index of air and N1 is the refractive index of core. So rearranging this equation, we have sine theta I by sine theta r. If you take the sine theta r to the other side, it goes to the denominator. So sine theta I divided by sine theta r. And this n naught, when it goes to the other side, it goes to the denominator. So sine theta I by sine theta r is equal to n1 by n naught. Let us take it as equation number 1. Shall I move?
Yes, ma'am.
Yes. So if theta I is increased, I hope you remember this diagram, right? This is very important concept which gives you the relation between the angle of incidence at the air core interface to the angle of incidence at the core cladding interface, right? So this is our angle of incidence theta I at air core interface at the point A, and this is the core cladding interface at the point B. Phi is the incident angle, and we already told that this angle will be equal to 90 degrees. So in this 90 degree, if this half angle is equal to theta r, the remaining angle will be equal to 90 minus theta r. Similarly, here also this angle will be equal to 90 degrees, and if this angle is equal to phi, this angle will be equal to 90 minus phi, right? And according to your geometrical relation, you say this theta r is equal to this angle, which is nothing but 90 minus phi, and this phi is equal to this angle, that is 90 minus theta r, right? So according to your Snell's law, if the angle of incidence increases, angle of refraction increases, right? So when theta I increases, theta r also increases, right? When theta r increases, 90 minus theta r will decrease, right? As a result, if 90 minus theta r decreases, this angle is equal to this phi. So phi will also decrease. So if you increase the value of angle of incidence at the point A, the angle of incidence at the point B will decrease, right? Let me tell you once again. If you increase the value of angle of incidence at the point A, the angle of incidence at the point B will decrease, right? That relation is given coherently with this equation. So let us go into the derivation. If theta I is increased beyond a limit, right? I hope you remember the relation between theta I and phi. When theta I is increased, phi will decrease, right? So when theta I is increased beyond a limit, phi will drop below the initial value of phi c. We had seen the illustration also with an example yesterday. So if theta I is increased, phi will decrease. But if theta I is increased beyond a limit, phi will decrease below phi c, right? When this happens, the ray will escape from the walls of the fiber. The ray will not be totally internally reflected. At the far end of the fiber, you won't get any light ray because the light ray will just get refracted away from the optical fiber, right? When phi, once it comes below phi c, the light will not be able to be transmitted in the fiber, but it will be simply refracted out of the fiber, right? The largest value of theta I occurs when phi is equal to phi c. I already told you that when angle of incidence theta I is equal to theta I max, when you increase the angle of incidence to a certain value called theta I max, phi will decrease to a certain value called phi c, right? So when theta I is equal to theta I max, phi will be equal to phi c, right? So let us try to find what is the value of sine theta r. In this equation, we have this sine theta r. So let us try to calculate what is the value of sine theta r in equation number 1. You already know this theta r is equal to how much? Could somebody tell me what is the value of theta r is equal to? Yes?
90 minus 5.
90 minus phi, exactly. Theta r is equal to 90 minus phi. So sine theta r can be written as sine 90 minus phi because these two angles are equal, right? This theta r will be equal to this 90 minus phi, right? So sine theta r can be written as sine 90 minus phi, and according to your trigonometric relation, you can write sine 90 minus phi is equal to cos phi, right? So instead of writing sine theta r, we can simply replace it with cos phi, right? And we have one more relation, that is this 90 minus theta r is equal to this phi, right? Please remember this equation also. So we have instead of theta r, we have 90 minus phi, and instead of phi, we have 90 minus theta r. These two relations you need to remember. So we can simply replace the sine theta r with cos phi. How come you write sine theta r as cos phi? Because theta r, the angle theta r is equal to 90 minus phi. So replacing this theta r with 90 minus phi, we have sine 90 minus phi. Sine 90 minus cos theta, sine 90 minus theta is equal to cos theta, right? Similarly, sine 90 minus pi is equal to cos pi. So let it be equation number 2. I hope you are all writing it down in your notebook. Sine theta r is equal to sine 90 minus pi, that is equal to cos pi. Let it be equation number 2. So let us try to substitute the value of sine theta r as cos phi, right? So let us try to substitute equation number 2 in 1. So sine theta I can be written as, right? So, see, from this equation, you can write sine theta I is equal to sine theta r into n1 by n0. And instead of sine theta r, we have sine theta r into n1 by n0, or from the relation to sine theta r is equal to cos phi. So let us replace the sine theta r with cos phi, right? So sine theta I will be equal to n1 by n0 into cos phi. This is our relation when you replace sine theta r with cos phi in equation number 1. Why you are replacing sine theta r with cos phi? Because from the sketch you can find that theta r is equal to 90 minus phi, and sine 90 minus phi is equal to cos phi. And hence you are replacing sine theta r in equation number 1 with cos phi. So that the resultant equation becomes sine theta I is equal to n1 by n0 into cos phi. So when this is the thing we have already perceived, that when theta I is equal to theta I max, phi will be equal to phi c, right? When theta I is equal to, let me go to a paint window. So what we had seen earlier is when you increase the value of this theta I, right? When the value of theta I increases, the value of phi decreases. When theta I becomes equal to theta I max, right? When theta I is equal to theta I max, phi will be equal to phi c, right? Phi will be equal to phi c. And if you increase the value of theta I to be greater than theta I max, what happens to phi? When theta I goes beyond theta I max, phi will be, yes? See, the relation between theta and I and phi is when theta I increases, phi decreases. When theta I is equal to theta I max, right? When you increase the value of theta I to theta I max, phi will decrease from phi to phi c, right? And if you increase the value of theta I to be above theta I max, phi will go below phi c.
5C.
Yes, phi will go below phi c. Is this favorable condition for total internal reflection to happen? Is this condition is favorable for total internal reflection? No. No, because when phi is greater than or equal to phi c, the ray will be contained within the fiber. If phi once, if it goes below phi c, the ray will be refracted out of the cladding, right? So this is the favorable condition for total internal reflection to happen, right? So when theta I becomes theta I max, phi is equal to phi c. So when when theta I is equal to theta I max, phi will be equal to phi c. So let us replace this theta I with theta I max and this phi with phi c, right? So when theta I becomes theta I max, phi will be equal to phi c. You can uh, write the condition reverse in reverse. When theta I is equal to theta I max, phi will be equal to phi c. Let us substitute this condition in the above equation. So instead of theta I here, I have written it as theta I max, right? And instead of phi here, we have phi c. Can you understand equation number 3? Yes?
Yes, ma'am.
Yes, I hope I can move on. So this is your equation number 3. Sine theta I max is equal to n1 by n naught into cos pi c. We already know the definition for critical angle, right? Critical angle pi c is equal to sine inverse of n2 by n1, right? So this is from the definition of critical angle. You can please write it down. After equation number 3, you can write from the definition of critical angle. From the definition of critical angle, phi c is equal to sine inverse of n2 by n1. Critical angle, from the definition of critical angle, phi c is equal to sine inverse of n2 by n1. What is n2 here? Yes?
Refractive index of cladding.
Yes, refractive index of cladding, that is rarer medium, and N1 represents refractive index of core, that is denser medium, right? So let us take this sine inverse term to the other side. So if the inverse term is taken to the other side, it becomes 1 by sine inverse, which can be written as sine, right? So when this sine inverse goes to the other side, it will become sine. So sine phi c is equal to N2 by N1. And we have a trigonometric, yet another trigonometric relation, which says sine square phi c plus cos square phi c is equal to 1. Actually, what we are going to do here is, in equation number 3, we are going to find an expression for cos phi c, and we are going to substitute it in equation number 3. Right? For that, we are starting with this phi c, and we are now about to calculate what is the value of cos phi c. Right? For that, let us consider the trigonometric relation sine square phi c plus cos square phi c is equal to 1. So cos square phi c will be equal to, if you take the sine square phi c to the other side, it will become 1 minus sine square phi c, right? Cos square phi c is equal to 1 minus sine square phi c. Or if you want the value of cos phi c alone, you can take root for this one, right? So sine cos phi c is equal to root of 1 minus sine square phi c. Now I hope we can substitute the value of cos pi z in equation number 5 in equation number 3, right? So cos pi z is equal to, and before substituting the value of cos pi z, let us try to substitute the value of sine square phi c here, right? We have already found what is the value of sine phi c. In equation number 4, we have the value for sine phi c, and let us substitute the value of sine square phi c over here. If sine phi c is equal to n2 by n1, sine square phi c will be equal to n2 square by n1 square, right? So let us, before substituting the value of cos phi c in equation number 3, let us try to substitute the value of sine square phi c also from equation number 4, right? So sine phi c is equal to n2 by n1. Sine square phi c will be equal to n2 square by n1 square. So let us replace the sine square phi c with n2 square by n1 square. So that the equation becomes cos phi z is equal to root of 1 minus n2 square by n1 square. Let us take common denominator by multiplying this n1 square with 1. So we have 1, let me do it in paint window. See, 1 minus n2 square by n1 square can be simply written as, you can just cross multiply this with 1. So you have n1 square, this minus n2 square divided by n2 square, right? You can replace 1 minus n2 square by n1 square with n1 square minus n2 square by n2 square, right? So you can see here. So n1 square minus n2 square by n1 square. Already we have a root here. So cos phi z is equal to root of n1 square minus n2 square by n1 square. So if this n1 square is taken out of the root, we have 1 by n1, right? Since it is in denominator, we have to write it as 1 by n1. So cos phi z is equal to 1 by n1 into root of n1 square minus n2 square. Can you follow up to this equation number 6? Can you follow what I'm saying?
Yes, ma'am.
Yes. So, yes, let me continue then. So, what is the next step we need to do? We have arrived at an expression for cos pi c. Now we need to substitute the value of cos pi z in equation number 3, right? So let us try to substitute the value of cos pi z over here in equation number 3. Please write it down. Substituting number 6 in 3. Substituting number 6 in 3. We have sine theta I max is equal to, already we have an n1 by n0 here, right? We have already an n1 by n0 here. So that n1 by n0 into, instead of cos phi c, we can write it as 1 by n1 into root of n1 square minus n2 square. So this n1 and n1 get cancels. Sine theta I max is equal to root of n1 square minus n2 square divided by n0. What is n0?
Refractive index of air.
What is the value of refractive index of air?
1.0.
1.00. It is simply 1, right? So refractive index of air is 1. So we can simply replace this n0 with 1, right? If your optical fiber is kept in air medium, you can simply write, you can simply ignore the value of n0 because it is equal to 1. You know the refractive index of air is equal to 1, and hence this expression can be written as, and instead of theta I max, we can simply replace it with theta A, right? We can replace this theta I max with theta A, and n0 is equal to 1. So this sine theta I max is equal to root of n1 square minus n2 square by n0 will become sine theta A is equal to root of n1 square minus n2 square, right? So this theta A, you call it as acceptance angle. When light ray falls within this angle, it will be totally internally reflective. Let me give you a diagram. See, this is the axis of the fiber. This is your core of the fiber, right? This is the core of the fiber. This is the other end of the fiber. So if this angle, you call it as theta A, right? This is equal to theta A. So theta A is the maximum angle, right? This theta A is equal to what? Theta I max, right? I have written this theta I max as theta A, right? Theta I max. And what is the relation between theta I max and phi c? When theta A increases, phi decreases, right? When theta A goes above, sorry, when theta I goes, when the angle of incidence goes beyond theta A, phi will become less than phi c, right? This condition should not happen. If this happens, light will just refract away from the cladding, right? Light will go away from the cladding. It won't be totally internally reflected. See, if this condition is satisfied, right, when theta A is greater than or equal to theta I max, right? Sorry, when theta A is less than or equal to theta I max, let me do it. When theta A is less than or equal to theta I max, this phi will be equal to or greater than phi c, right? So this is the condition for total internal reflection. When this theta A, I should not write it as theta A, I have to write it as theta I, right? When theta I is less than or equal to theta A, phi will be equal to or greater than phi c, right? So if this condition is satisfied, light will be totally internally reflected into the medium. If this condition comes off, when the angle of incidence goes beyond this angle, right? If the angle of incidence is greater than theta A, right? This is your theta A. If the angle of incidence of the light ray is greater than theta A, light will be simply refracted off because the critical angle, I mean the angle of incidence at the core cladding interface goes below critical angle, right? So this is the maximum angle, right? This theta A is the maximum angle uh, below which when light falls on the air core interface, it will be totally internally reflected. So how will you define this acceptance angle? How will you define critical angle? Could somebody give the definition for critical angle? Yes? If this is theta I, if theta I is greater than phi c, what happens? Yes. If theta I is greater than theta c, what happens? Total internal reflection. That is the second condition for total internal reflection, right? If angle of incidence is greater than critical angle, total internal reflection will happen, right? So this is the definition for critical angle. Let me tell you once again the definition for critical angle. It is the angle of incidence above which total internal reflection happens, right? Theta I is the theta c, sorry, pi c is the critical angle. Critical angle can be defined as the angle of incidence above which total internal reflection happens, right? Similarly, how will you define theta A? It is the maximum angle below which total internal reflection happens, right? So when theta I is less than theta A, phi will be greater than phi c, right? So this is the condition for total internal reflection. When once this theta I goes above theta A, phi will go below phi c, right? When phi go below phi c, total internal reflection will not happen. When this condition exists, total internal reflection will not happen. This is the favorable condition for total internal reflection. Whenever you have the value of this angle of incidence below this theta A, the angle at core cladding interface will be staying above phi c, so that total internal reflection takes place. So let me define the acceptance angle or angle of acceptance. Acceptance angle is the maximum angle below which light will be totally internally reflected. Let me ask you a question. What happens when angle of incidence, right? When angle of incidence is equal to acceptance angle. Let me tell you once again, if angle of incidence is less than acceptance angle, phi will be always greater than phi c, and hence total internal reflection takes place, right? This is the condition for total internal reflection. And if theta I is equal to theta A, what happens? Could somebody give me an answer for this question? When theta I is equal to theta A, what happens? No answers. When theta I is equal to theta A, phi will be equal to phi C. When phi is equal to phi C, what happens? Oh my God, you didn't grasp a single concept. So when angle of incidence is exactly when angle of incidence theta I is equal to phi c, the light will graze the interface between core and cladding. Instead of going total internal reflection, the light will undergo a refraction at the core cladding interface. Right? We have seen three cases when angle of incidence is less than critical angle. Partially light will be reflected, partially it will be refracted. And when the angle of incidence is equal to critical angle, the light will be grazing the interface between core and cladding. And the third case is when the angle of incidence is greater than critical angle, light will be totally internally reflected. These concepts you need to remember to understand what is acceptance angle. Right? Let me tell you once again, when angle of incidence is greater than, less than acceptance angle, the light will be totally internally reflected back because phi will go above phi c. Whenever phi is greater than phi c, then you can expect total internal reflection. And see here, when the value of angle of incidence is equal to theta A, phi will be equal to phi C. Here phi is the angle of incidence at the core cladding interface. When this angle of incidence is equal to critical angle, the light will just graze the interface between core and cladding. And let me ask you another question. Let us see, at least you answered this question. So when angle of incidence goes beyond this theta A, what happens to phi? When theta I is greater than theta A, what happens to phi?
Phi is less than
Phi will go below phi C. Will total internal reflection take place?
no, ma'am.
No, it is our first condition. When angle of incidence is less than critical angle, the ray will be simply refracted into the space. It will be no more internally reflected, but it will be simply refracted out into the space. Right? Please try to remember these concepts. So theta A, you can write theta A is equal to C, sin theta A is equal to root of n1 square minus n2 square. So theta A will be equal to sine inverse of root of n1 square minus n2 square. And this theta A, you call it as acceptance angle. N1 and N2 are the refractive indices of core and cladding respectively. So how will you define the acceptance angle? It is the maximum angle at or below which light can suffer total internal reflection. How will you define critical angle? Critical angle is the angle of incidence above which total internal reflection takes place, and the acceptance angle is the maximum angle below which total internal reflection takes place, right? So at critical angle, if the angle of incidence is equal to acceptance angle, then the light ray will graze the interface between core and cladding. For proper total internal reflection to take place, the angle of incidence should be always less than acceptance angle, right? That's the maximum angle at or below which the light can suffer total internal reflection is called acceptance angle, right? If you see in 3 dimensions, right, in 2 dimensions, I am writing it as a single theta, right? But if I consider it in 3 dimensions, you will be having a cone, right? When light falls within this cone, the light will be totally internally reflected, and when light falls outside this cone, it will not be totally internally reflected, right? So this angle will be equal to 2 theta A, right? This, see, this angle is equal to theta A. When light falls within this theta A, it will be totally internally reflected. If angle of incidence goes beyond this theta A, if a light ray falls at this angle, this is your normal. If a light ray falls at this angle, this will not be totally internally reflected, right? So you can define acceptance angle, right? This is your acceptance angle. Acceptance angle is defined as the maximum angle below which total internal reflection takes place, right? Similarly, if you consider it in 3 dimensions, right, this is the axis, this is your theta A. If I consider it in 3 dimensions, I'll be having a cone. This is equal to 1 theta A, this is equal to another theta A, the whole will be equal to 2 theta A, right? So a cone which is having a solid angle of 2 theta A is called acceptance cone, right? When light falls within this cone, it will be totally internally reflected. But when light falls outside this cone, this light will not be taken for total internal reflection, right? So the cone with the solid angle of 2 theta A around the axis, you call it as acceptance cone. Why you call it as acceptance cone? Because light falling within this cone will be accepted for total internal reflection, and the light which is falling outside the cone will be simply refracted, right? So you can see here. So thus the maximum angle at or below which the light can suffer total internal reflection is called acceptance angle, and the cone is referred to acceptance cone. This is 2 dimensional angle. If you consider it in 3 dimensions, you'll be getting a cone, right? That you call it as acceptance cone. And acceptance angle is the maximum angle that a light ray can have relative to the axis of the fiber, so that it can propagate down the fiber, right? So if the incident light ray goes beyond this acceptance angle, total internal reflection will not happen, and you cannot expect light to propagate down the fiber. It will be simply refracted out of the fiber, right? So in 3 dimensions, the light ray contained within the cone having an angle of 2 theta A are accepted, right? So if you consider in 3 dimensions, when the light falls around the axis within the angle of 2 theta A, it will be accepted for transmission through the principle of total internal reflection. Therefore, the cone you call it as acceptance cone, and the light incident at an angle beyond theta A refracts through the cladding, and the corresponding optical energy is simply lost. So it is obvious that larger the diameter of the core, larger is the acceptance angle, right? So if you have a less core diameter, I'm sorry. See, if the core diameter is very less, right? This is the diameter of the core. This is the axis of the fiber. The value of theta A will be less, right? This is the value of theta A. Let us consider this is the value of theta A, right? So if I have a larger diameter fiber, right? So this is my fiber, and this is the axis of the fiber. So now this is my theta A. I'm sorry. So now this is theta A, right? If you consider this theta A, this will be certainly larger than this theta A. So what is the relation between theta A and the diameter? If diameter of the core increases, right? If diameter of core increases, the value of theta A also increases. Please remember this. It might be a part A question. Let me complete the session with this. So one of the factor that affects this acceptance angle is core diameter, right? If the diameter of the core is less, acceptance angle is less. If the diameter of core is larger, then the acceptance angle will also be larger, right? Can you understand what I'm saying?
Yes, ma'am.
Yes. So that is what you call it as acceptance angle. So the session ends by 35, right? 12:35 or 25?
12:30, ma'am.
12:30. Okay. I have 2 more minutes. Let me try to complete this also. A very little concept. Numerical aperture refers to the uh, light gathering capacity of the fiber, right? How much light the fiber gathers. That capability you call it as numerical aperture, right? How will you define acceptance angle? It is the maximum angle below which light will be totally internally reflected. And how will you define numerical aperture? Numerical aperture is the light gathering capacity of the fiber, right? It is the light gathering capacity of the fiber, right? So the acceptance angle and so numerical aperture is defined as sine of acceptance angle. If you know the value of acceptance angle, you can able to find this numerical aperture by taking sine of that value, right? So there are two definitions for numerical aperture. The first definition is numerical aperture is the light gathering capacity of the fiber, and this numerical aperture can be defined as sine of acceptance angle, right? You know acceptance angle theta A is equal to sine inverse root of n2 square minus n1 square by n0, right? So this is your value of sine theta A, right? Sine theta A, or let us go with this equation. Theta A is equal to sine inverse root of n1 square minus n2 square. To be precise, I have to write this equation as sine inverse of root of n1 square minus n2 square divided by n0, right? N0 is the refractive index of air. So numerical aperture is sine theta A. So how will you write it? Sine of theta A. The value of theta A is equal to sine inverse root of n1 square minus n2 square. So numerical aperture is equal to sine of, right? Sine of, instead of theta A, I have written sine inverse root of n1 square minus n2 square. This sine inverse and this sine, they will cancel with each other. So simply you have numerical aperture is equal to root of n1 square minus n2 square. What is n1? Yes, what is n1?
Refractive index of core.
Refractive index of core, and n2 is refractive index of cladding. Please remember these two formulas. Theta A is equal to sine inverse. What is the formula for theta A? Theta A is equal to sine inverse of, please remember these two formulas for solving problems. Sine inverse of root of n1 square minus n2 square divided by n naught, right? This is the proper formula, right? If the fiber optic cable is kept in air, you can simply discard this n naught. If it is kept in water, then you have to use the value of this N0, right? And what is numerical aperture? Numerical aperture is equal to sine of theta A, or I can simply write root of N1 square minus N2 square divided by N0, right? If the fiber is kept in air, you can simply discard this N0, and numerical aperture will be equal to root of N1 square minus N2 square, right? So numerical aperture determines the light gathering ability of the fiber. It is a measure of the light that can be accepted by the fiber. How much of light will be gathered by the fiber? How much of light will be accepted by the fiber, right? That will be given by this numerical aperture. Numerical aperture depends only on the refractive indices of core and cladding. You know the expression for numerical aperture is root of N1 square minus N2 square. So this numerical aperture depends only on the value of the refractive index of core and refractive index of cladding. So Na depends only on the refractive indices of core and cladding materials, and it does not depend on the physical dimension of the fiber, right? Please remember this point. Acceptance angle will be depending upon the diameter of the fiber, right? Acceptance angle will be proportional to core diameter. It depends upon the dimension of the fiber. If the diameter of the core increases, acceptance angle increases, right? But this numerical aperture does not depend upon the physical dimensions. It depends only on the refractive indices of core and cladding, right? And the normal value of numerical aperture ranges from 0.13 to 0.50, right? This is the typical value for numerical aperture of an optical fiber. The large Na implies that the fiber will accept large amount of light, right? If numerical aperture is higher, you can say that the light gathering capacity of the fiber is also higher, right? Let me stop with this. You please go through your textbook for acceptance angle and numerical aperture, and if there is any clarification that you need, you can always we can have a discussion, right? Let me stop the session. If there is any doubt, you can clarify it, else you can please leave the session. Thank you.
Thank you, ma'am.
Thank you,
Thank you.
ma'am.
Thank you, ma'am.
Thank you, ma'am.
Thank you, Pa.
Thank you, ma'am.
Thank you.